Hello, welcome to this lecture. And in this lecture, we will see the conventional tubes and their limitations. Okay, so what are the limitations of the conventional tubes? So, before going to the limitations, first of all, I would like to uh, introduce for 2 minutes what are the conventional tubes. So, conventional tubes are basically tubes, vacuum tubes. Okay, so these vacuum tubes may be of uh, triodes, tetrodes, pentodes. Okay, these may be the vacuum tubes. Okay, so also if we want to see, then we can see in the diagram also. This is the conventional tube. So triode may be there, tetrode may be there, pentode may be there. What is the difference? In all these uh, figures, two things are common. One is anode, and another is the cathode. Okay, and cathode is along with the uh, this element and heater. Okay, so this is electron emitter. If this is the filament and heater, if we will heat the filament, okay, electrons will be emitted. So vacuum tubes were there. Vacuum tubes were the diode, tetrode, and petrode. Okay, so diodes were contains the two terminals. One is anode, another one is, and triode contains three terminals. One is anode, one is cathode, and one is the control grid. Okay, here tetrode, one anode, one cathode, and two grids, two control grids. One is screen grids, and another one is control grid. Okay, and in pentrode there is an anode, there is a cathode, and there are three grids. Okay, suppressor grid, screen grid, and control grid. So there may be a, so what does these grids, oh, what is the functioning of this grid? Okay, so grids are used for controlling access. Okay, grids are used for the controlling access. Grid voltages will be the controlling voltages. So what will be the voltages applied to this grid? That will be the controlling voltages. And actually what happens when the electron is going from this uh, cathode to the anode, then to control the electron from going to cathode from anode, there are so many grids. Okay, here it is one grid, here it is two grid, and there are three grids. Okay, so there are three terminals, so it is triode. There are four terminals, so it is tetrode. Here it have five terminals, so it is a tetrode. But these uh, conventional tubes, vacuum tubes, have several limitations at the microwave. Okay, so there are several limitations. Means uh, these conventional tubes will not work properly at the microwave frequency. So, what are the limitations? We will see one by one. So, um, mainly there are six limitations or vacuum tube. Okay, so conventional tubes fails to operate above 1 gigahertz. These conventional tubes or vacuum tubes are fails to operate above 1 gigahertz. One the microwave frequency starts from 1 gigahertz. So 1 gigahertz and above, these tubes will not work because there are 6 reasons behind it. So spray reactances are of two types: inter-electrode capacitance and lead inductance. And second one is the transit time or angle effect. Third one is the gain bandwidth product limitation. Fourth one is the skin effect or conductor losses. And fifth one is the radiation loss. And sixth one is the dielectric. So these 6 limitations are there for the conventional tube. We will see one by one. So first one is the inter-electrode capacitance. Okay. So here it is a triode, as we have seen in the previous slides, that there is a anode, oblique plate, there is a cathode, there is a heater and an element that will emit the electron. So, and here it is a so controlling voltage we can apply here. Okay. So there are grid means inter-electrode capacitances means this one. Here it is when we connect these devices to another devices, there is a soldering. Okay, so this is the electrode. This soldering thing is nothing but the electrode. Okay, so because of it behaves as a metal plate, it also behaves as a metal plate, it also behaves as a metal plate. So there may be capacitance between this grid and plate. So this is known as CGP. There may be uh, capacitance between grid and cathode. So this is CGK. Okay, and this is the capacitance between anode and cathode or plate at cathode. So this is known as CP. Okay, so the capacitance between two electrode is called the electrode capacitance, and this is given by epsilon A upon T. Okay, so let us suppose there will be some capacitance between this grid and this plate. There will be a capacitance between this grid and this cathode, and there will also be a capacitor between plate and cathode. Okay, so how much this impedance is offered due to this capacity? So Xc is equal to 1 upon 2 pi Fc. So C is fixed because the this one uh, the area of this uh, electrode, that is soldering, is fixed. Okay, the area of this is also fixed, the area of this is also fixed. So C equal to epsilon A upon T, and Xc is equal to 1 upon 2 pi Fc. All we know, C is constant and F is varying. As F increases, this Xc decreases. Since capacitive impedance is inversely proportional to the frequency, Xc is equal to 1 upon F. So at microwave frequencies, Xc will be very small because of this inversely relationship. F increases, Xc decreases. So Xc behaves as a source. The voltage of grid and cathode becomes equal, and hence no amplification by the triode is done at the microwave. Okay. Now, second one is the lead inductance. The basic building block or the concept behind it is uh, a wire, okay, a linear wire acts as a inductor, acts as a inductor, and it, it is written in the first line here. Inductance exists for a conducting wire. All we know, inductance uh, of conducting wire behaves as an inductor. Okay, so what happens? For a straight wire, inductance is given by L upon mu A, where L is the length of the wire, A is the cross-sectional area of the wire, and mu is the permeability of the material of which this wire is made up of. Okay, so um, all these um, leads will be connected from this uh, tube with a wire. Okay, so these wires work as the behaves as an inductor. Okay, so let us suppose there is a fixed inductor. Lg is there, grid inductance, Lp is there, plate inductance, and Lk is there, cathode inductance. Also, we know that the XL 2 pi Fl, the impedance offered by the inductance is given by 2 pi Fl. Okay, so where L is the length of the wire, mu is the permeability of the material, and A is the cross section of the wire. That is very simple. As the frequency increases, the inductive reactance increases. The inductive reactance increases. XL is directly proportional to F. So at microwave frequencies, XL is very large. At microwave frequency, XL is very large. Hence, there will be impedance matching problem at the input as well as at the output. Okay. So this is the formula of XL 2 pi FL. So XL will be directly proportional to the frequency. So at microwave frequency, since frequency is very large, XL will also be very large. And if the inductance or impedance will be very high, then impedance matching problem will be there at the input as well as the output. Thus, there will be reflections from the input as well as from the output port. Okay, because of these reflections, a small fraction of the input reach to the terminal for amplification. Okay, so because of the high impedance, impedance matching problem will be there. Okay, so impedance will not match at the input, and it will also not match at the output. So what happens because of this? So there will, if impedance mismatching will be there will be reflections from the input and as well as from the output. And because of these reflections, a small fraction of the input reach to the terminal. So very small amount of the signal reach to the terminal for amplification. So amplification becomes very small. Okay. So there is another problem. So inductance and inductance of the cathode is common to both the grid and anode circuit. This provides the regenerative or feedback path. Okay, so if this provides the feedback path, these inductances and inter-electrode capacitances forms unwanted tuned circuit. If L and C will be there in the series or in parallel, it will form a tank circuit or tuned circuit. So it forms unwanted tuned circuit which produces parasitic oscillation. Okay, so unwanted oscillations are there because of this because of this inter-electrode capacitances and inductance. Okay, so one is this one, inter-electrode capacitances and inductance, and another very important is the transit time effect. Another one is the transit time effect. So what is the transit time? First of all, the transit time is the time taken by an electron to travel from cathode to anode. Okay, so transit time is nothing but the time taken by an electron to travel from cathode to anode. Okay, also this transit time may be written as this d upon v naught, because the velocity of this electron is v naught. Okay, and the separation is d. So distance traveled by the electron is d, and the velocity with which it has traveled from here to here is v naught. Okay, so what will be the transit time? The time taken by an electron to reach the anode from cathode is given by the distance d upon v. Okay, this. Also, the transit angle will be given by omega tau, and tau is nothing but d upon v naught. So this will be omega d upon v. Okay, so it is a very simple mathematics. At low frequencies, the transit time is very small. Okay, transit time, actually transit time is not a small. Transit time remains the same because it is the time taken by an electron to reach the anode from the cathode. But what happens, uh, t is the time period of the applied input signal. This capital T is the time period of the applied input signal, and it is nothing but V by F. So if this F is very small, okay, if this F is a small, T will be large. If this capital T is large, then this tau is smaller than this tau, because at lower frequencies this is large, very large. So with respect to that, because this is large, so the transit time will be less than this t. So there is no any problem in reaching the electron from here to here. But at higher frequencies, okay, so at higher frequencies, what is it does? The t is lesser than the tau, means the time period of the applied input signal is lesser than the transit time. Means as the electron starts from here, it goes here, okay, and the cycle changes because this time period is very much less. because this F has increased very significant. So if this frequency is very high, so this time period will be of the applied input signal will be very very small. So what will happen? The electron in positive half cycle, okay, in positive half cycle, electron will go from here to here, let us say. And now the polarity has changed. So now it is a negative cycle, negative voltage. So this electron will force an opposite force and it will travel from here to here. It may reach to the cathode again, okay, or if it will not reach to the cathode, then it will oscillate anywhere here, like it will not go to the cathode, it will not go to the anode. So it is very very difficult for us. The grid potential during the negative half cycle removes the energy given to the electron in positive half cycle. Okay, so that is very simple. In positive half cycle, electron moves from cathode to anode, and in negative half cycle, electron moves from anode to cathode. If electron is not able to reach the anode in positive half cycle, it will return back towards the cathode in negative half cycle. Thus, electron will oscillate between the cathode and the grid. Okay. So, to minimize this effect, okay, transit time effect, the distance or separation between the anode and cathode should be very very small, so that it reaches to the anode in very small time. And high voltage must be applied. So there are two things that apply high voltage so that its velocity increases, and uh, take a very smaller distance between anode and cathode, so that D will be a small, so it will be reaching. Tau will also be very small. Okay, so voltage must be applied, but this will increase the inter-electrode capacity. Okay, so if this separation is decreased, this electrode separation has also decreased, so electrode inter-electrode capacitance will increase. That is not desired. Now, another limitation of the conventional tube is gain bandwidth product. So at microwave frequencies, these tubes start resonating. For resonating circuit, gain bandwidth product is constant. माइक्रो फ्रीक्वेंसी पर ये रेजोनेट करने लगता है और रेजोनेंट सर्किट के लिए गेन बैंडविड्थ प्रोडक्ट कांस्टेंट होता है. If we want to increase the gain, we will have to sacrifice the bandwidth. We will have to sacrifice the bandwidth. So that is very simple. So gain and bandwidth. Gain bandwidth is constant. Now, if we want to increase this gain G, so this bandwidth will have to decrease because the multiplication is the constant. So if it will increase, so it would have to decrease. So if we want to increase the gain, okay, the bandwidth will automatically decrease. Now skin depth. This is the formula for skin depth. Okay, skin depth is equal to 1 upon pi mu sigma f. So as f increases, okay, this skin depth decreases. So here, as f increases, skin depth decreases. If skin depth decreases, so the uh, current will start following on the surface, okay, on this surface. So if the current will start flowing on the surface, then the net cross-sectional area of the electron flowing will be decreased. So if the effective cross-sectional area will decrease, so resistance will increase, okay, because R equal to rho L upon A. If this effective area, cross-sectional area of the wire will decrease, this R increase, and if R increases, conductor losses increase. Okay, so this is very simple. It's in-depth problem. It increases the conductor loss. So what is radiation loss? Okay, at microwave frequencies, the wavelength is very, very small. And if wavelength is small, okay, so and its antenna will have very small size. At microwave frequencies, antenna size will be very, very small. And the electrode pins behaves as the antenna, and it starts radiating. So if radiation will be there, there will be radiation loss, because some of the energy have lost in terms of radiation loss. So at higher frequency, if we will use these conventional tubes, then radiation losses will be there. And last one is the dielectric losses. Dielectric losses is what, as the frequency increases, loss tangent of the material will increase. And if the loss tangent of the material will increase, then dielectric losses will increase, because dielectric losses directly proportional to the loss. Okay. So I hope you must have understood that about the limitations of the conventional tubes or vacuum tubes. Okay. So in the next lecture, we will see the uh, microwave tubes, okay, types of microwave tubes, linear beam tubes, cross field tubes, okay, O type of tubes and M types of tubes, okay. So be in touch with us and subscribe our channel to get the latest videos, okay. Thank you for watching.